Hello, everyone. The last topic from chapter 16 that I wanted to take a little bit of time to discuss was the Lewis acid-base theory. The Lewis acid-base theory focuses on the reaction between acids and bases a little bit differently than the ones that we have looked at before. Everything we've looked at so far would still be encompassed in this theory, but this will be a larger theory that also encompasses other reactions that are convenient to think about as acid-base reactions, even if they don't have a proton in some cases. So in the Lewis acid-base theory, we're thinking of the lone pair that we often think of as accepting the proton as being the primary thing that is guiding how these reactions take place. So we do not even have to have hydrogen atoms for this particular theory to work. With Lewis acid-base theory, we think of the electron donor as what we call the Lewis base. So Lewis base is an electron donor, and then the electron acceptor is the Lewis acid. Okay, so just stop for a minute and think that this is consistent with what we've already been talking about. And that the base has these electrons that are grabbing the protons. The only thing different here is that it doesn't have to grab a proton. It can be grabbing something else instead. So the Lewis base will be something that we can describe as being electron rich. So it has a lot of electron density based on its molecular structure. We call this a nucleophile, something that has a lot of electrons and is looking for some kind of a positive charge to share those with. The electron acceptor would be then electron deficient. It doesn't have enough electrons. There's a reason why it wants to get more electrons. So we call this one an electrophile. So we're defining this acid theory based on what the electrons are doing. So Lewis acids are things that are electron deficient in some way. So they either don't have an octet, so the molecule does not have an octet, or there is some portion where you have an electronegative atom that is sucking all of the electrons away from something else. They do need to have a place where they can accept those electron pairs. So basically an empty orbital is where that would occur. For a proton, that's the 1s orbital, right? So with a proton, you had hydrogen with one electron. If it lost that electron, there's nothing in the 1s orbital. So that is where it would be accepting that electron pair. And boron trifluoride, there's an empty 2p orbital, and that is where it could accept that electron. You'll notice that boron trifluoride is our first example of an acid that does not have a hydrogen. Okay, so this is a Lewis acid. And so our definition has expanded to include molecules such as this. We often can think of these highly charged metal cations that we've already discussed as having empty orbitals where they can accept electrons as well. So when we said, you know, things like aluminum +3, iron +3 that are dissolved in water are functioning as an acid, this is how another way we can explain that as well. And then if you have an atom that is connected to some highly electronegative atom and it can have additional bonds to it, it can behave as a Lewis acid. For the Lewis base, we need to have a location where we have electrons that the molecule is willing to somehow share with another atom. This is very consistent with the Bronsted-Lowry definition of a base. There we were saying, you know, you have something accepting a proton. Well, it can only do that with electrons. So this is very consistent with that theory. So we're not really changing a lot for the base when we look at Lewis theory. We can specify, though, with this definition that we must have a lone pair of electrons somewhere. that those electrons are then what is being donated. In general, if we have something that's an anion, it will be a better Lewis base than a neutral atom because we have more electrons there. Okay, so we're showing nitrogen compared to nitrogen with a negative charge. I'm not sure what's going on with those lone pairs there. I think we're not showing all of them, I think, in that case. Oh, I see. We're showing I think that's just the formatting. So there's more going on to these two nitrogens than what we're showing in this PowerPoint. But essentially, negative charges will have greater base properties than no charges. Here we're looking at a Lewis acid-base reaction. So the base is donating a pair of electrons to the acid, and that will generally result in the formation of a covalent bond. So we have ammonia. We know ammonia can act as a base. We've seen it do that already. But in this case, instead of accepting a proton, we're having it react with something else. So we're having it, in this case, react with boron trifluoride. And as that happens, we form a covalent bond because the nitrogen is sharing its electrons with the boron. So again, we have an acid-base reaction with this definition that contains no protons. Now, there are some hydrogens in the ammonia, but they're not behaving as acids. They're still connected in the same way. You'll also just kind of notice, again, that the Arrhenius and Bronsted-Lowry acid-base definitions are included within the Lewis acid-base definition. So this is just a broader definition that we can use to include additional reactions that do not contain protons. I'm not going to spend too much time on this other than to say that if you are planning to go on to take organic chemistry, this Lewis acid-base definition becomes very important. It's actually one of the most important things in organic chemistry is understanding when something will behave as an acid and what it will do, or when something will behave as a base and what it will do. Part of that is showing the movement of electrons because that's what we're focusing on in terms of how the reactions take place. And we do that with these curved double arrows. I'm not going to get into those details here, but if you do go on to take organic chemistry, you'll see these come up again. And if you want to kind of get a jump start on understanding those, you can kind of look in more detail on what your book has to say about that. So that is kind of the last chunk of chapter 16. Please let me know if you have any questions.